Welcome to this lecture on measuring gravity, where we travel from apples to atoms and everything in between. On this slide, you can see classical concepts like Newton's apple, large-scale detectors such as LIGO, and emerging quantum sensors, all tied together by a single theme: understanding gravity with ever greater precision and different technologies. This slide shows where precise gravity measurements really make an impact, from finding subsurface resources to tracking environmental change. Gravity helps reveal hidden reservoirs and cavities, monitor magma and water table shifts, test fundamental physics, and underpin metrology by defining mass standards and vertical datums. So these measurements support both practical exploration and big-picture science. Here we explain the classic mass on a spring gravimeter, which relies on Hooke's law and equilibrium shifts. Tiny gravity changes move the mass and change the spring extension. The cartoon diagrams show how a deltag shifts equilibrium, and in practice, instruments need thermal stability, vibration isolation, and careful calibration to reach sensitivities around 1 microgal after drift correction. This slide covers precision absolute gravimetry using free-falling corner cubes and interferometry. In a vacuum, the falling cube experiences pure gravitational acceleration, while a Michelson interferometer times fringe zero crossings to fit a parabola and extract G with roughly 3 microgal accuracy, with FG 5 class instruments anchored in quiet, temperature-stable labs for reference networks. Rotating gradiometers measure gravity gradients by spinning paired masses on orthogonal arms, producing torque proportional to curvature while rejecting common mode accelerations. The rotating signal modulation allows airborne mapping of salt domes and ore bodies, making these sensors ideal for detecting subsurface anomalies during surveys where spatial resolution and motion-tolerant operation matter. Atom interferometry brings quantum precision to gravity measurement through a 3-step process: laser-cooled atom preparation and freefall, counter-propagating light pulses forming a matter wave interferometer, and phase difference readout that yields G with nanogel-level repeatability. The approach reduces systematic errors, has no mechanical moving parts, and offers promising routes for spaceborne and fundamental physics missions. Micro-machined silicon gradiometers use chip-scale seesaw levers with differential capacitive readout to bridge portability and high spatial resolution. These batch-fabricated sensors aim for gradient sensitivities near 10 E per root Hertz, while operating under 1 G, enabling compact deployments on drones, in boreholes, or even on planetary landers for detailed subsurface mapping. Accurate gravity mapping depends on careful data collection and correction. Networks of stations provide stable base readings, instrument drift is removed, and raw data are corrected for latitude, free air, bouguet, tides, and terrain effects. Those corrections isolate local anomalies, whose amplitude and shape help reveal density contrasts and the geometry of buried features for interpretation. Residual bouguet maps highlight density anomalies, with highs suggesting dense basement or ore bodies, and lows indicating voids or sedimentary basins, as the illustrations show. Integrated modeling then combines borehole logs and forward 2D or 3D modeling with inversion to estimate depth, shape, and density, guiding the selection of drillable targets with confidence. Looking ahead, next-generation sensors and networks promise dramatic gains: entangled, atom arrays, superconducting gradiometers, and hybrid MEMS optical devices aim for 0.1 microgal and 0.01 E resolution, while swarms of drone-mounted sensors could map cities in 3 dimensions, and satellite constellations would track hydrology and climate with frequent revisits, opening new frontiers in monitoring and exploration. In summary, gravity measurement has evolved from simple spring balances through pendulums and absolute gravimeters to quantum interferometry, each stage improving sensitivity and portability. These methods provide geological insight, identify economic resources, and test fundamental physics, and the next wave of quantum and MEMS technologies promises to democratize high-precision gravimetry for many new applications.